Welcome to part 2 of our lecture series on the Insight Spreadsheet Development Environment. In part 1, we covered the basics of how spreadsheets work, mostly to solve mathematical problems using spreadsheet programming syntax. In part 2, we will introduce you to how to use this foundation to build machine vision applications using the Insight Spreadsheet Development Environment. If we step back about 20 years ago, the choice to use a spreadsheet as the programming methodology was a strategic decision based on three key drivers. First, vision applications usually require a lot of data inputs, and vision tools also produce a lot of data as outputs. Several research papers from the 1990s showed that a spreadsheet was the most efficient method of manipulating data, or put another way, of passing data into functions and for processing the results. Every cell has the potential to be a variable, and to connect a variable to a function, you just need to click on the cell to create a cell reference. Next was the widespread base of users who knew how to use a spreadsheet. Even if we don't think about the mechanics of how a spreadsheet works, or think that creating a spreadsheet is actually writing a program, that's what we're doing. Given the number of people who can use a spreadsheet is far greater than the number of formally trained software developers, the spreadsheet enables vast numbers of users to create programs. And finally, spreadsheets are incredibly powerful and flexible, especially in our case, since Cognex provides a large set of machine vision specific functions. Next, the Insight spreadsheet is event-driven. When we're building a spreadsheet, just the act of adding a new function or changing an input parameter will cause the spreadsheet to update, meaning we can see the results immediately. Doing the same task in a programming language like C++ would require us to recompile the program before seeing the effects of the change. And, just like Microsoft Excel, changes ripple through the spreadsheet automatically, and we don't need to concern ourselves with program flow. We can organize our spreadsheet any way that we want to. Now at this point, you may be wondering about what happens in production mode when the vision system is deployed in a factory and when a person isn't interacting with the spreadsheet. How does it work, or how does it update? We'll talk about that more in a few minutes. But before proceeding, one important note here is to mention that we're not going to spend too much time covering the details of machine vision algorithms. This information is covered in detail in our Insight training classes. Our primary goal is to show you how the mechanics of using a spreadsheet can be used to build a vision application. Here's an example of an Insight spreadsheet program. This is a completely functional vision application. This program contains a total of 54 cells, 24 of which are just text labels which serve to help document what the program is doing. In the space of 30 cells that are actually doing something useful, the program is acquiring an image, locating the part within the image, finding two edges and measuring the distance between them, counting consecutive rejects and displaying a message on the screen if there are 3 rejects in a row, and writing images of failed parts to an FTP server with a custom file name that includes the name of the camera plus a time and date stamp. There is no other programming paradigm where you can create such a complete vision application in just 30 lines of code. Before we dive into the details of the program, let's take a 50,000-foot view of a typical machine vision application performing, in this case, an inspection task. Vision systems, like most automation systems, rely on some external stimulus to start an action. So we need to configure what type of event will initiate a program cycle, which could be a simple photosensor detecting that a new part is in front of the camera. Once the part is in place, we need to acquire an image and present the image to the vision tools for analysis. Most applications start by locating the position of a workpiece in the image. This step is useful since it can reduce the complexity and cost of hard tooling to orientate and present the part in a fixed location. Once we locate the part, we can provide the location information to subsequent vision tools so they can automatically adapt to the position of the part. We call this fixturing. Next, we perform the actual inspection task by defining what areas are to be inspected as well as parameters for the machine vision algorithms, also called vision tools. In a generic sense, Cognex vision tools produce results data, which must then be analyzed or evaluated to determine good versus bad. This usually involves some sort of if-then-else logic to generate a binary or good-bad result. Finally, we need to communicate the results of our inspection to some external device so that the part can either proceed or be removed from the production line. This device may be a simple actuator that diverts parts into a reject lane on a conveyor, or a PLC which may be needed to track the part to a downstream reject station. There are certainly other things we can do in a vision program, but these 6 steps are the foundation of most inspection applications. If, for example, we wanted to use machine vision to guide a robot pick-and-place operation, we would need to add a calibration operation in step 2, and we would usually omit step 4 since the goal is simply to locate the part. Now let's take a closer look at how we can accomplish each of these steps within a spreadsheet programming environment. We start with an acquire image function, and by convention we place this function in cell A0 for reasons I'll get to in a minute. Just like in Excel, the expression bar shows us the name of the function and the cell shows us the result. In this case, the small rectangle next to the word image denotes that the data returned from the acquire image function is a data structure of type image. We don't need to know too much more about this data structure other than it's the means by which we get the image into the spreadsheet so that it can be consumed by other vision tools. The structure also contains information such as the X and Y dimension of the image and whether it's grayscale or color. But as I said, these are usually not needed. In order to actually acquire an image, we also need to configure an input stimulus. This is accomplished by opening the property sheet for cell A0, which you can do by simply double-clicking on the cell. Here we see the list of input parameters for our acquire image function, the first of which is the trigger mode. The default is camera, which means we are going to wire a discrete input directly into the camera's trigger input pin. The second most common option is industrial Ethernet, meaning an Ethernet message from a PLC using the PLC vendor's preferred factory floor protocol, such as Profinet from Siemens, Ethernet IP from Rockwell, or CC-Link IE from Mitsubishi. Once we have the external stimulus configured, the spreadsheet will update cell A0 whenever this stimulus is received. Our next step is to locate the part we want to inspect. In order to do that, we must first train the vision system to look for a particular pattern or feature on the part. Pattern matching is the most common way to locate a part, so we need to know the name of a function that we can use to perform this task. We do this by looking in the toolbox, which is analogous to the Excel insert function option. Here we can see a large collection of machine vision functions organized by categories and subcategories. In this example, we start in the category Vision Tools, then under Pattern Match we see a list of function names. At this point, we can either simply double-click on the function name or drag and drop the function name into a cell in our spreadsheet. As soon as the function is inserted into the spreadsheet, the property sheet will open to allow us to configure the input parameters for pattern finding. The first parameter of every vision tool is the image parameter, and here we see, by default, the image parameter is an absolute cell reference to cell A0 denoted by the syntax $A, $0. Remember on the previous slide, I mentioned the convention of using cell A0 for our acquire image function? Now we see why. Every time we add a new function to the spreadsheet, the image parameter is automatically referenced to cell A0 as a shortcut, so you don't have to set this parameter up every time. And as we saw earlier, by using the absolute reference syntax $A, $0, it means if we ever cut and paste this cell to a different location in the spreadsheet, it will always retain the reference to cell A0. The next parameter we need to set is the pattern region, which is the location in the image where we want to train our pattern. To define the region, we simply click on the parameter name, then one of the icons in the toolbar, which will then allow us to pick and place the region graphically in the image. Finally, there's one other important parameter in our train pattern function called the train event. Since we have created a dependency between this function by referencing cell A0, in normal spreadsheet behavior, we would expect this cell to update automatically every time a new image is acquired. But of course, we don't want that to happen. So the train event acts as an override and prevents the pattern from retraining when A0 is updated. The trained pattern will only be updated when we open its property sheet and click the train event button, or if we define a different event, which we will learn about later. Once we've trained a pattern, the next step is to insert a corresponding find pattern function, which can also be found in the toolbox. Just like with our train pattern tool, the image parameter for our find pattern tool automatically references cell A0. We also need to tell the tool which pattern to look for. So in this case, we can simply reference cell A2, which returns a pattern structure from the train pattern function. There are a lot more parameters associated with pattern finding, but aside from the find region, the default values are often all you need to use, or at least they're a good starting point. As you see in cell B4, this function also returns a pattern data structure which contains details about the found pattern. You probably also noticed several additional cells to the right of the find pattern function. These are a combination of labels in row 3 and functions in row 4 that extract data from the data structure called patterns. The Insight IDE is smart, and as long as there is sufficient space to the right of the find pattern cell, these cells will be auto-populated with the data that is most commonly needed later in the vision application. If there isn't sufficient space, you can always add these cells manually, or you could simply perform an undo operation and then start over by placing the find pattern function into another location in the spreadsheet that has ample room for these cells. Let's take a closer look at how to extract information from results data structures. Here you can see in cell C4, there is a function called getX, which has two input parameters. To discover what data is contained in a data structure, we can look for the list of available getter functions in the toolbox under the category Vision Data Access. Here we see the data that can be extracted from a pattern structure. For this particular getX function, the first input parameter is a cell reference to the data structure holding the data. The second parameter is an index value, which is optional, and used here by default because it's possible for a pattern finding tool to locate more than one instance of a pattern. For convenience, cell B4 was automatically populated with the index value 0, so we can simply reference this cell in our getter function. Before we continue, now is a good time to circle back to some things we learned in part 1 of this lecture series. Based on what we know about dependencies, what causes cell A0 to update? In our case, it's an external camera trigger as we configured earlier in the acquire image function. Okay, now what causes cell A4 to update? Here, our function has two cell dependencies to cells A0 and A2. So if either cell A0 updates with a new image, or if a new pattern is trained in cell A2, then our find pattern tool in cell A4 will update. It will also update if we change an input parameter, which we can do by opening the property sheet. As your spreadsheet program increases in complexity, it can be difficult to see all of the dependencies highlighted in the expression bar. So to make things easier, there's a function called cell auditing that will overlay arrows showing inputs to a cell as well as outputs from a cell. We didn't mention this earlier, but this function also exists in Microsoft Excel and can be enabled by clicking on an icon in the toolbar. Once we've located the part, the next step is to choose the appropriate vision tools to inspect the part. For the purpose of this example, which vision tools we use are not that important, so here we're using a histogram tool which measures brightness in the image. The measure of brightness might be useful to determine if something is present or not. In any case, since we're using a pattern finding tool to locate the part, we need a means to pass the found location of the pattern finding tool into our inspection tool. This process is called fixturing, and we do this by referencing the X, Y, and angle results of our pattern finding tool in the fixture parameter of our histogram tool. By doing this, our inspection region will automatically move to the correct location over the part if it moves from image to image. We can accomplish this very quickly by double-clicking on the fixture parameter name in the property sheet, then by selecting, in this case, cells C4, D4, and E4 with a single sweep of our mouse, and these three cells will automatically be inserted as cell references into our property sheet. A more tedious way to do this would be to double-click on the X parameter name, select cell C4, then double-click on the Y parameter name, followed by selecting cell D4, and repeat again for the theta parameter. Or we could even just type the cell references directly into the property sheet. This is a good time to also remind you of something we covered in part 1 about the dependency tree. In this case, we have 4 dependencies, and we can better understand the significance of how the dependency tree is managed. Our external event will cause A0 to update. Then we have 3 getter functions extracting the X, Y, and angle values for our fixture. You can see here why it's important that our histogram tool in cell A7 will wait until all 4 cells, A0, C4, D4, and E4 have been updated, since we don't want our histogram tool to update multiple times. It will only update after all of its predecessor dependencies have been updated. After the vision tools complete their analysis of the image, we need to apply some good versus bad decision criteria. The toolbox contains a collection of math and logic functions, and one of the most commonly used functions is called the in-range function, which compares a numerical value to an upper and lower limit. This function returns a value of true, or a numerical value of 1, when the value is within the upper and lower range, and returns false, or a numerical value of 0, when it's outside the range. Now we could just create a cell reference to one of the values in the histogram tool as the first parameter of the in-range function, followed by 2 numerical constants, but I want to call your attention to another powerful feature of the Insight spreadsheet. In this example, cells G7 and H7 contain what are called edit-in controls, which are also commonly referred to as up-down controls. The toolbox contains a large list of graphical controls that can be embedded directly into cells in the spreadsheet. We'll learn a lot more about controls in part 3 of our lecture series, but here you can see by using edit-in controls, we can quickly and easily change our upper and lower limits without having to change the constants in the actual in-range function. Once we've derived a good versus bad decision in our spreadsheet, we can output that decision to a discrete output line from the camera or as part of a message to another piece of automation equipment, such as a PLC. In this case, we've chosen a right discrete function that will reference the value produced by the in-range function. Notice in the expression bar, we've added a not function ahead of the cell reference of the in-range function in cell I7. This not function inverts the Boolean logic and produces a 1, which turns the output signal on when the inspection fails. Notice also that the right discrete function also references cell A0. This is the event parameter for the right discrete function, meaning that every time a new image is acquired, the right discrete function will execute whether or not the data input value changes. This sounds like wasted execution if our input data doesn't change, but we do this for an important reason. Discrete outputs from the camera can be configured as pulsed outputs, meaning we can control the duration of the on signal. We might do this to limit the amount of compressed air being used to blow a product off the production line and into a scrap bin. In the case where we have 2 consecutive bad parts, we will need to turn the output back on, so the event input assures we will do this even if the input data doesn't change, which would be the case if we had 2 consecutive bad parts. Using the edit control, we can change the high limit to cause a fail condition. Then we can see the in-range result changes from 1 to 0, and the right discrete, which inverts this value, will output a 1, which turns the output signal on. So here you see the benefits of using edit controls. They provide a quick and easy way to test our program logic. And at this point, we've created a completely functional vision application. Congratulations! You now know how to build a simple but complete machine vision application using the Insight spreadsheet programming environment. Let's recap what we learned in part 2 of our lecture series. First, we learned the 6 common steps needed to build a vision application. Second, we learned how to add vision functions found in the toolbox into our Insight spreadsheet. Third, we learned how to use the property sheet to set up parameters for our vision tools and other functions. Fourth, we learned how cell referencing is used to pass data from the spreadsheet into functions. Fifth, we learned how to use getter functions to extract data from result structures into individual cells in our spreadsheet. And sixth, we learned how to configure an external stimulus to serve as the event to trigger spreadsheet updates. Coming up in part 3 of this lecture series, we'll learn more about some unique features of the Insight spreadsheet environment that extend the power and flexibility to build some very sophisticated machine vision applications. Thank you for watching.